Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Good day. Welcome to Pastor Victor's Academy. I'm glad you're watching. I believe you'll learn a lot from this video. So do well to pay attention as we go on. In my last video, I talked about energy, work, heat, and the first law of thermodynamics. We also saw the energy balance equation. Then in this video, I'll be talking about thermodynamic cycles. A thermodynamic cycle is a sequence of processes that begins and ends at the same state. So when we have a sequence of processes that begins and ends at the same state, we call it a thermodynamic cycle. So here we have a thermodynamic cycle comprising of 5 states. There is state 1, state 2, state 3, state 4, state 5. Then we're also having 5 processes. That's process 1, 2, process 2, 3, process 3, 4, process 4, 5, and process 5, 1. So process 1, 2 is the process that leads from state 1 to state 2. Process 2, 3, the process that leads from state 2 to state 3. The same thing applies here, and here. Now, what makes this a cycle? Because it comprises of different processes that leads back to the initial state. So it began with 1, 2, then we'll have 2, 3, we'll have 3, 4, we'll have 4, 5. Then from 5, we returned to the first state. Now looking at the energy balance equation, we're having that change in E is equal to Q minus W, and that's equal to change in KE plus change in PE plus change in U, which is equal to E2 minus E1. Remember we said that kinetic energy, potential energy, internal energy, they are all properties of a system. And here E2 minus E1 means the sum of all these energies for state 1, then, and that for what? State 2. So we said energy is the property of a system, meaning that it is not a path function. It doesn't depend on the path, rather it depends on the state of the system. So for state 1, we are having E1, U1, the same thing for KE1, PE1. Then state 2, we also have E2, U2, KE2, PE2. Then we'll have that for state 3, state 4, state 5. Now let's look at what happens. To calculate change in E, we'll be saying E2 minus E1. Now, assuming we want to know the total change in the energy of the system as it moved from state 1 to state 2 and back to state 1, we would say change in E for the first process, that's P12, plus change in E for the second process, P23, plus change in E for the third process, P34, plus change in E for the fourth process, P45, plus change in E for the fifth process, P51. Now remember that change in E12 is E2 minus E1, and we have E2 minus E1. Then plus, for the second one, change in E23, that's E3 minus E2, E4 minus E3, E5 minus E4, and E1 minus E5. That's for the last process. Now, by the time we remove all the brackets we have, E2 will subtract this one, that's E2 plus minus E2, that will give us 0. Then minus E1 plus E1, that will give us 0. Then E3 minus E3, that will give us what? 0. E4 minus E4, that will what? Give us 0. E5 minus E5, that will also give us what? 0. So you can see that the total change in energy is equal to what? 0. So when a system moves from a particular state to another state and returns back to the initial state, the total change in energy is equal to what? 0. So you don't say, we begin to look at energy to and fro. No. Energy is a property of a system and depends on the state. So the question is, what is the state of that system at that point? So when you know the state of the system at that point, then you can calculate the change in energy. So everything here is just the same thing as saying E1 minus E1, which is equal to 0. Why? Initially we are state 1, then now we also are state 1. So the total change in energy will be what? E1 minus E1. And that gives us what? 0. So what happens to this formula? What that means is that the total change in internal energy is also what? 0. Then the total change in potential energy is 0. The total change in kinetic energy is also what? 0. But that does not mean that Q is equal to 0 or W is equal to 0, because these are part what? Functions. So if we should go with this, we'll be having that 0 is equal to Q minus W, which means that Q is equal to what? W. So for a thermodynamic cycle, Q is equal to W. Now to show that this is a cycle, we simply say Q cycle is equal to what? Work cycle. So for a thermodynamic cycle, Q cycle is equal to work cycle, and change in E cycle is equal to what? 0. So we can say Q cycle minus W cycle is equal to change in E cycle, and that is equal to what? 0. We'll be looking at different types of thermodynamic cycles, and the first one is the power cycle. It is a kind of thermodynamic cycle where heat energy is converted into mechanical work. The system involved in this kind of thermodynamic cycle do not convert all the heat energy supplied to it into mechanical work. Some amount of energy is released to the surroundings as heat. Hence, the net work output of the cycle is the difference between the heat supplied and the heat rejected. So what that means is that when heat is supplied to the system, some amount of that heat supplied is rejected. So the work cycle now becomes the heat supplied minus the heat rejected. So here we have it. Here is work cycle Q in minus Q out, where Q in is heat supplied from the hot body. Here we have our system. Then we have cold body. So here heat is supplied to the system. Then some amount of that heat is given out to a cold body. So we're having that work cycle is equal to Q in minus Q out, which is equal to what? Heat cycle. Examples, we have Otto cycle that's used in petrol engines. Then we have diesel cycle used in diesel engines. Now we want to look at thermal efficiency. Thermal efficiency is a measure of how well a system converts heat into useful work. In other words, it is the percentage of the heat supplied that is converted into useful work. Now here we have the symbol for thermal efficiency, which is equal to work cycle over Q in. So you can see that we're interested in Q in, not Q out. That's the heat supplied to the system. How much of it was converted to what? Useful work. Here we're having thermal efficiency is equal to work cycle over what? Q in. From here, we know that work cycle is Q in minus Q out. So we can substitute for work cycle, and we're having Q in minus Q out over Q in. Now, when Q in is divided by Q in, we'll be having 1. Then minus Q out over what? Q in. So we can say that thermal efficiency is equal to work cycle over Q in, or 1 minus Q out over what? Q in. Now, since we're having Q out over Q in, and the system will definitely reject what? Some amount of heat, it means that thermal efficiency will always be less than what? 1. Now, if we are to convert this to percentage, 1 would mean 100%, meaning that thermal efficiency of every power cycle is always less than 100%. The next one is refrigeration and heat pump cycles. These are types of thermodynamic cycles in which heat is transferred from a cold body to a hot body by means of external work. So when heat is moved from a cold environment or a cold body to a hot body, then we are talking about a refrigeration cycle or heat pump cycle, depending on the one we are looking at. Now, Q out is always greater than Q in because the external work is converted to heat to ensure that heat flows into the hot body. Otherwise, heat will naturally flow from the hot body to the cold body. Now look at this. For power cycle, heat is flowing in from the hot body and flowing into what? The cold body. That's the natural direction of heat flow. Heat will flow from a point of higher temperature to a point of what? Lower temperature. Then the result of this is that you are having work cycle. And that will be the difference in Q in and Q out. So we're having Q in minus Q out equal to what? Work cycle. So the arrow is inwards from this direction and outwards in this direction. Then work cycle is outwards. So the difference between these two will give birth to work. But in the case of refrigeration and heat pump cycles, what are we having? All the arrows are what? Reversed. Now, here we are having Q out and we're having cold body. But for the cold body, we're having what? Q in. That means heat is coming from the cold body and entering into what? A hot body. And the result is that work must be done on the system to achieve this. Because naturally, heat will not flow from a cold body to what? A hot body. It's just like having a glass of hot water in your hand. Instead of heat flowing from the glass of hot water to your body, heat is flowing from your body to the hot water. That's not possible. It's against what? The natural direction of heat flow. So here we are having heat flowing from cold body to hot body. That's through the system. Then for that to be achievable, work must be done on the what? On the system. So that's what happens in refrigeration. We supply energy to the freezer and is able to absorb heat from the container and move it into the surroundings. So the same thing applies to what? Heat pump cycle. So here work cycle is now equal to Q out minus Q in. In this case, work cycle is Q in minus Q out. Whereas in this case, work cycle is Q out minus what? Q in. Why? Because Q out is greater than Q in. You may be wondering why. That work done on the system generates heat. So Q in plus that work done is what gives birth to what? Q out. So in other words, another way of writing this formula is to say that Q out is equal to work cycle plus what? Q in. So this work cycle makes it possible for heat to flow from the cold body to the what? To the hot body. So look at this. Here we're having T out and we're having T in. This is the hot body, this is the what? Cold body. Now, if you begin to look at it as two different heights, what it means is that T out is greater than what? T in. So if you have a plank connecting these two and a ball on that plank, naturally the ball will roll from T out to T in. Why? This one is at a higher what? Elevation. But what does work cycle do? It's just like moving T in from its initial elevation to a higher elevation. So in that case, the temperature rises to a point that is enough for this ball to move from this elevation to what? To this elevation. So that's what happens here. The work done on the system forces the system to move heat from the cold body to the hot body. Now the next question is, what is the difference between refrigeration cycle and heat pump cycle? Both have the same working principle. That's the diagram we have here. Q in from a cold body into the system, Q out into what? A hot body, then work cycle inwards. So the same working principle. But the difference is now our area of what? Concentration. Now in the case of refrigeration cycle, our concentration is on this part. For example, you have your freezer. What does your freezer do? It removes heat from whatever you put inside. And as that heat is leaving, it is moving into what? The surrounding. Now, the same thing for a room. Let's assume you are in a room that is hot and you turn on the AC. What will the AC do? The AC will remove heat from that room and send it to the what? To the surroundings. Now, it keeps doing that. It gets to a point that the temperature of the room will be lesser than that of the surroundings, yet it will keep removing heat from what? From the room. That's the work of the AC. So the focus of refrigeration cycle is on the cold body, whereas the focus of heat pump cycle is on the hot what? Hot body. Now, in the case of heat pump cycle, what does it do? Let's say the environment is cold, and as a result, you turn on your heater. What will your heater do? It will keep absorbing heat from the surroundings that is already cold into what? Into the room. So the temperature of the room begins to increase. Then the heater is still what? Absorbing heat from the surroundings and giving it to the what? To the room. To keep the room warm. So when you're in the room is warm. But when you step out of the room, the environment is what? Is cold. So that's it. The focus of heat pump cycle is on the hot body, whereas the focus of refrigeration cycle is on the cold body. We are looking at how much heat is supplied to the room, but in this case, we are looking at how much heat is taken from what? From the room. Finally, we are looking at coefficient of performance for refrigeration cycle and heat pump cycle. So coefficient of performance, the short form is COP. It is a measure of how efficient a refrigeration or heat pump cycle is. It tells us how effectively the system uses work, that is the energy input, the energy supply to the system, to absorb heat or give out heat. So here we are having coefficient of performance, COP. Now for refrigeration cycle, we are having beta is equal to COPR, that's COP R. The R here is a subscript to show that we are talking about refrigeration, is equal to Q in over what? Work cycle. Now, why do we have work cycle under? Because this is the energy supplied to the system. And remember that energy is supplied in the form of what? Work. But in the case of power cycle, the energy was supplied in the form of heat. That's Q in. So that's why we're having work cycle under. Now, why do we have Q in above instead of Q out? Why we have Q in is because we are looking at the energy absorbed. That's energy entering into the system. Because the focus of refrigeration is the heat supplied to the system or heat absorbed by the system. So we are looking at how efficient the system is in absorbing what? Heat. So Q in over work cycle simply means how much heat can the system absorb because of the work done on it. That's what it's talking about. Now in the case of heat pump cycle, that's we're having a gamma equal to COP HP, that's COP HP heat pump, equal to Q out over work cycle. So work cycle is still the denominator, but now the focus is on what? Where the energy is going to. So we are looking at how much heat the system is able to supply because of work done on the system. That's what Q out over work cycle means. So we're having B equal to Q in over Q out minus Q in. Remember, for this kind of cycles, work cycle is Q out minus Q in, unlike power cycle, where we have Q in minus Q out. So work cycle is Q out minus Q in, and in that case, we'll be having Q in over Q out minus Q in, and for this one, we'll be having Q out over Q out minus what? Q in. So that brings us to the end of this video. Thank you for watching. Please do well to like, comment, share, and subscribe. Your subscription is very important to me and also help me share. I want to reach more students. God bless you as you do that. Once again, thank you for watching.